Now, it's important to keep that in mind because people tend to, for some reason, if it's a helium balloon, substitute helium in here. Okay? Well, it is not the helium that's causing the buoyant force. It's the air that's been moved out of the way that's causing the buoyant force. Now, it just so happens that helium is less massive than is air. So when you replace the force of air with helium, the weight of the helium is less than the weight of the air that you've moved out of the way, and so the buoyant force is upwards. Okay? If you blow up a balloon with regular air, and you kind of hold it in air, it doesn't float. Because you got air inside that says move the same air outside. Unless the air is heated air, which is your hot air balloons, then the air inside the balloon is less dense because it's hotter. And because the density is less, this is smaller, so this is smaller. With fluids like water, okay, it's the fluid that's being pushed out of the way. It's the water that's being pushed out of the way that supports the weight of the steel ship. Okay? Provided that you push more water out of the way than the ship weighs, it will float. This was a big issue back beginning of World War II. They were running out of steel, so they decided they were going to make ship hulls out of concrete, which was a good idea because concrete's nice and strong. It was easy to get. The only thing is that they forgot to seal the concrete. So when they first put the ship in the water, it floated. The concrete absorbs water. So after a couple of days, the concrete would absorb enough water that the weight of the concrete hull and the water that it absorbed was bigger than the buoyant force, and they sink to the bottom.
What? You think a concrete boat was smart?
They found out what they were doing wrong
just
pretty
like
quickly. Some of your
a lot.
larger tankers today have concrete hulls.
So there.
But the concrete is sealed so that the integrity of the weight of the hull doesn't change.
Wood.
So, Archimedes Principle. The buoyant force equal to the weight of the fluid displaced. Now, in your textbook, you've got the density chart at the bottom. Okay, there's this obscure little formula here. Okay? Density of gases, okay, because gases, if you take a look on the atomic scale, gases are made up of atoms and molecules that are relatively far apart. Okay? Since density is mass per unit volume, if you crowd more particles into a smaller space, you're going to end up with more density. Now with solids and liquids, it's not a big issue because with solids and liquids, the spacing between your molecules is very limited to start with. But with gases, the spacing can be great between your particles or can be very small, depending on the pressure. And so there's a formula at the bottom, okay, which will give you the density of a gas relative to pressures and temperatures. So the density here is given for pressures PO, which is 1 atmosphere. So normal atmospheric pressure, okay, would have these densities, which are the densities in the chart. If your pressures are higher than atmospheric pressure, then you would have to add in that pressure, okay, times your 273.15, which is your standard temperature, okay, then divide it by pressure at PO, which is your 1 atmosphere, 1.013 times 10 to the 5th, plus your temperature plus standard temperature to get your new density, which would then be your density that you would use for buoyancy problems. So the bottom line is, if you're not at standard temperature and pressure, you need to use this formula to find out what your density is, because your density is not the same as what's in the chart. The chart densities for gases are gases at standard temperature and pressure. So if you're dealing with a problem, and your textbook deals with those problems, okay, that are not at standard temperature and pressure, use the formula at the bottom to solve for the new density at the given standard, at the given temperature and pressure, and then use that density to solve your problems. And as I said, you'll get some of those in the problem set for tonight. The problem set for tonight's, actually the work, that's the problem set for tonight's not out of the book. The problem set for tonight's not working.
Alright, I think that's about it.
Are you sure? Oh, turn it off. What do you